spanning sets, so in R2 and R3. So what we're talking about is we're going to talk about how vectors can be a combination of any other set of vectors as long as they're not collinear or linear vectors in both two-dimensional space and three-dimensional space. So a lot of words combined didn't really sound like it made a lot of sense, but let's try to figure out what they're talking about. They say x, or vector x, has the points of 4 and 23. So let's just say that, oh, well, this is about 4 and this is about 23. This is just a rough sketch, okay? So here's our vector x in 2 space. What they're saying is show that it can be a combination of either of these 2 vectors put together. Okay? So I'm going to give them names. Even though they didn't give them names in this question, I'm going to call this vector A, vector B, vector C, and vector D. So what it's saying is this vector x can be a combination of A and B, okay? And it can be a combination of C and D. Now, when we first draw it, it may seem a little odd. Let's try A. A is at -1, so we'll say that's here, -1 and 4. That's probably something like that. I'm trying to draw it roughly to scale. So that would be vector A. And vector B would be 2 and 5, a little higher, something like that. Okay? So obviously we add the 2 together, we won't get vector x, but I can put scalars of each of these. And I can find some scalar for both vectors that will eventually, when I combine these 2, whether it's adding or subtracting them together, I will get a resultant vector of x. So what they're saying is any vector can be a combination of any 2 other vectors as long as they're not parallel. If they're parallel to each other, then we aren't able to get that movement around the graph. We have to stay in one linear line. Okay? Just like, and again, these are just rough sketches. Oh, that one's even harder to draw. 1 and 0, so that's vector C. And vector D, excuse blue, that's a nice color. -2 and 1, that's something like that. I know those are really hard to see. It's very combined. Anyways, we can combine these vectors to make, again, a resultant vector of x. So we're going to prove this. And the way we're going to prove that is I'm saying that for vector A, some scalar named A multiplied by the vector itself A plus some scalar of B for vector B will be equal to 4 and 23. Okay? So I'm saying I can put some scalar to B, some scalar to A, add them together, and it will give me that resultant vector in the end. So what I'm going to do to solve this is we're going to kind of work a little backwards. We're going to substitute this in, so I get -A, okay? And we're going to have -A and 4A plus 2B and 5B is equal to 4 and 23. Okay? Well, we know when adding components together, we take the x values and add them together. I'm going to zoom in a little. Oops. There we go. So I take my x values and add them together. So I know that -A plus 2B is equal to what? Anyone know? To 4. That's right. This A, -A plus the 2B will be equal to our resultant x. So it is equal to 4 in this case. And in the other one, we know that 4A plus 5B, sorry, I got a little confused there. When we put those together, it's going to be equal to our resultant vector value of 23. So now what I have is 2 equations. Just kind of like I did in that question before, I have 2 equations here. And we have 2 variables in each equation. Well, this goes back to our grade 10 math where we just go to substitution. We're going to substitute, set the values equal to A, B, or C. In fact, I'm going to use elimination. Does anyone remember elimination? No? Yeah? Okay. So I'm going to, you know what, we'll go to substitution because I think that's what most people are used to using. So we'll go to substitution. -A is equal to 4 subtract 2B, which means the value A is equal to 2B minus 4. Okay? So I know I can substitute the value of a for this. Okay, so that's still my equation 1. I'm going to sub it into equation 2. Well, equation 2 is 4, and I'm going to replace the letter a with this value here. So we get 2b minus 4 plus 5b is equal to 23. We distribute the 4, 8b minus 16 plus 5b equals 23. It's a bit choppy right now. This is going to give us 13b is equal to 39. B is equal to 3. So the scalar for vector b would be the number 3. And then we're going to plug this back into equation 1 to solve for what a would be. Negative a plus 2 times 3 is 4. Negative a is equal to 4 minus 6. Negative a equals negative 2. A equals 2. Okay with that? I went through that fast enough. So in the end, what that's saying is 2. And remember, my components for vector A were negative 1 and 4. And then plus 3b. Where is it? 3, that's my value of b. And vector b was, or the components for vector b was that, is equal to 4 and 23. Okay? So let's kind of try to make sense of this. Oh, yes. There you go, 4 and 23. What that's saying is, okay, a to the power of 2, so essentially 2a, whatever that vector is, and 3b, okay, when combined together, are going to get us a vector that's of the same value and magnitude of vector x. So we put some scalar of it. And we can do the same thing again with these guys here. Okay. In fact, I want you guys to try it because I'm just going to write the answer quickly up on the board in a moment. I want you guys to give it a try. Okay. Using those vectors, vector c of 1 and 0 and d of negative 2 and 1, get me a resultant vector of 4 and 23.